in order to compute the properties for the natural channel for classification, you have to be able to determine the wetted perimeter and the total area. So you see this slide shows a bankful cross-section at a riffle in which it has been split up into 7 smaller areas and 7 wetted perimeters. So the total area, you'll notice, is a combination of triangles, rectangles, and trapezoids, is simply the sum of the total areas of each of the subsections. Likewise, the wetted perimeter around the perimeter is the sum of the wetted perimeter of the 7 subsections. If you're calculating a wetted perimeter, it's simply using the coordinates and the distance formula. So we would be calling these the stations and the elevations. And you can see there's the Pythagorean theorem giving you a wetted perimeter for that particular sample of 8.94 feet. The area, here you see a sample calculation of a trapezoidal area. You need obviously 2 points to do it, so right at the end, the first area will be equal to 0. Now, the bankful top width, examining the data, would be 36 minus 13, giving you a 23 feet of width. The bankful maximum depth, you examine the table, and you see the bankful maximum depth is 5 feet. If we multiply that by 2, that's the depth at which we will determine the flood-prone width. The overall bankful cross-sectional area up to the bankful level, not above it, is the sum of these 4 areas, which gives you the 58 square feet. The bankful wetted perimeter up to 727 is the sum of these 4 quantities, which gives you 25.21 feet. The bankful hydraulic radius is simply then the area divided by the wetted perimeter to give you a hydraulic radius of 2.30 feet. The bankful hydraulic depth, which is also the mean depth, is the 58 square feet divided by the 23 feet of top width. This is the parameter that is used in the Rosgen classification system. The flood-prone width at 2 times the bankful depth, you would look at where the stationing is, and that would be from 1 foot to 57 feet, giving you a flood-prone width of 56 feet. The entrenchment ratio is calculated as the flood-prone width divided by the bankful width. 56 over 23 gives you 2.43. The width to depth ratio is the bankful width divided by the hydraulic depth. So that would be the 23 divided by the 2.52, giving 9.13. The stream length we determine over about 20 to 30 bankful widths. So that would have been done in the survey. So in this case, the stream length was 552 feet divided by the valley length of 345 feet gives you a sinuosity of 1.6. Now, taking the width to depth ratio, the entrenchment ratio, and the sinuosity, you could then go to the Rosgen classification chart and see this is a letter E channel. The number comes from the fact from the D50 is actually a cobble. The largest size gravel is 64 millimeters. So in this case, according to Rosgen, this would be an E3 channel. We can then compute the average water surface slope of the stream as being the vertical drop divided by the stream length. So 3.3 feet, which have been surveyed, the 552 feet which have been surveyed, gives us an average water surface slope at base flow conditions of 0.006. The average water surface slope of the valley at base flow would be the vertical drop over the valley length, which would then be the 3.3 divided by the 345 is 0.0096. Now, estimate of Manning's N for the stream type from figure 11.8. You look up the E3 and it would be an estimate of 0.032, assuming it was not controlled by a vegetative influence. The bank full velocity can simply be estimated using Manning's equation. So putting in the hydraulic radius and the average water surface slope at bank full conditions, and then the velocity would be 6.27 feet per second. The bank full flow rate can be estimated simply then as the bank full cross-sectional area, which is the 58 square feet times the bank full average velocity. So the estimated bank full flow rate is 363.4 CFS. And then we would get the bank full Froude number, which you can see would then be 0.696. Notice this part of the calculations is similar to what we've been doing through the entire class. Now, let's assume we're going to replace this natural channel by a straight constructed channel with a bottom width of 10 feet and 3-to-1 side slopes. So if we take our flow rate, our roughness, and our slope, which would be now the slope of the valley, it gives us a normal depth of 2.84 feet, a cross-sectional area, 52.49 square feet, top width of 27.02 feet, a wetted perimeter, 27.95 feet, a Froude number of 0.876, and an average velocity of 6.93. The hydraulic depth, which would be the mean depth, would be the cross-sectional area divided by the top width. So that gives a hydraulic depth of 1.94 feet. So now we have a sinuosity of 1. The top width of the flood-prone area, we would simply get the top width in the channel. And then we have an entrenchment ratio of 1.63 and a width to depth ratio of 13.9. If you happen to look on the Roskin classification chart, the closest thing to this is an F. It would actually be an F3 channel. You can see the effect of straightening out. You've increased the velocity, increased the Froude number. You've altered the top width to depth ratio. This is all very significant when it comes to being able to transport sediment. So when you replace a meandering channel with a straight prismatic channel, here are some of the effects. You increase the average bottom slope, the average velocity, and the erosion potential. You deny access to the floodplain for the storage of excess water, removal of excess sediment, and removal of woody debris. And you decrease aquatic habitat.